In this video, we are going to learn what a linear spline is, and let's go ahead and import some data here to work with. I'm going to go ahead and use that coronavirus data that we've been working with. And again, we just only want to highlight the week and the total number of cases. Okay. It has been imported, so we can exit out of here. And remember, we always need, if this is coming in from an Excel document, it's inserting actually a table here, and we want to turn that into an array. Okay, and so there's our data, and let's just separate this into x's and y's. So how about x is equal to the data that is in the first column, and y can be the data from the second column. And now in the linear case, a spline is just going to be a linear line that connects one point to the next. Okay, so we're connecting all of our points with linear splines. And technically, the way that the plot function works in MATLAB, at least graphically, we can see the spline. Let's go ahead and plot this. So I need to hit editor and then run. And so you can actually tell that this isn't perfectly smooth, and it's because each point is being connected again by some linear line. Okay. But the question is, how could we create this? Okay. And I think we're going to learn something kind of interesting that we can do as far as indexing our functions go. Okay. Let's go ahead and get started. So let's start our for loop. So for I equals 1 to something. And just to make this a little bit more general, let's go ahead and check the length of x. Okay. And remember, the length of both of these should be the same. Okay. We need just as many x coordinates as we need y coordinates. Okay. So once we get that length, the thing I want you to note is that if we have n data points, it's going to require n minus 1 linear lines to connect all those data points. Okay. Now, a general, or a way that we can actually index our functions, so in other words, we can make like a list of functions, is you can do y, curly bracket, I, curly bracket. Okay. So this for loop is going to create a y1 function, a y2 function, a y3 function, and so on. Okay. And so to create these functions, the first thing that we're going to want is the slope. Okay. Well, to get the slope, we'd want to find the change in x and the change in y, right? Change in y over change in x. So how about y of I plus 1 minus y of I. So there's our change in y divided by our change in x. So x of I plus 1 minus x of I. Okay. Next, we'd want to multiply by x minus a, right? So is what I'm trying to tell you is our variable here is going to be x. And just so we don't mix up these lowercase x's and y's, why don't we call this big Y here, and our variable, let's call that big X, and let's begin this with an at big X. Okay. So we have big X minus, okay, and it should be the x coordinate, so how about x of I? And the last thing we need is plus y of I. And all I'm doing here is using the equation for a linear line. Let me write the form that we're using here. Y equals m times x minus, how about we say x naught plus the function value at x naught. So that would just be y naught. Okay. This is what we're using here. Okay. All right, so we have our function, okay, or our mini functions. Let's plot them. So plot, okay. And since we're going to actually plot these as a function, let's use fplot. Okay. So we'll do fplot y sub I, okay, or the ith function there, and over what interval? Well, let's just take x of I plus 1, or sorry, x of I to x of I plus 1. Okay. And since we're going to be plotting these all in the same graph, we're going to want to hold on and an end. And let's go ahead and give this a run. I'm probably going to want actually to get rid of this right here. Let's go ahead and hit run. Okay. And you can see actually, and they're separated by color, but you can see all those linear lines connecting each point. The downside here is this isn't very smooth, okay, doing linear splines. Okay. Well, if we do quadratic splines, is what we'll be able to do is we'll be able to ensure, it's going to take a little extra work, but we'll be able to ensure that at least the first derivatives match at the points where these connect, so there won't be an abrupt change in slope. And if we even go a step further and go to cubic splines, then we can ensure that not only the first derivatives match where they meet, but also the second. So then there's not going to be an abrupt change in concavity between the points, and it'll be even smoother. And so that's what we'll do in our next videos. We'll look at quadratic splines and then cubic splines.